Hey guys, good morning. Assalamu alaikum. Welcome back to grade 11 physics / chemistry by Inspired Teens. In today's lesson, we are going to be starting with chemistry. Okay, we're going to be doing molecular structure. Okay, sorry for the delays, but let us carry on. Okay, so we're going to be discussing molecular structure. Okay, the first thing we're going to be discussing, a lot of the stuff on the onset of this lesson is going to be like theoretically based. Okay, so molecular structure. Knowing the structure of a molecule enables you to determine its physical and chemical properties. The structure mainly depends on the type of chemical bond that exists between the atoms that the molecule consists of. Okay, so what we gather from this is that the structure depends basically on the type of bond. Okay, so let's learn more about bonds. Okay, chemical bonds. A chemical bond, the net electrostatic force that two atoms sharing electrons exert on each other. That's what's defined as chemical bond. Okay, bonding occurs when valence electrons are shared between two atoms or transferred from one atom to another. Valence electrons correspond to the group number of an element on the periodic table. Okay, so just give me 1 second. Okay, let's see the definition of valence electrons. Valence electrons are electrons in the outermost energy level of an atom that take part in the bonding. Okay, so this is important for us to remember. I'm sure we've learned about this before. But yes, our valence electrons, these are our electrons in the outermost part of the atom, okay, that take part in bonding. And the ones on the inner, which we don't need to know anymore, are the core electrons. Okay, so if this is an atom, right, our valence electrons will be found on the edges. Okay, remember it has like multiple layers. Okay, and closer towards the center is where we'd find our core electrons, but on the edge we find our valence electrons. Okay, so just keep that in mind. And why are valence electrons important, especially when we discuss chemical bonds? Because valence electrons are the electrons that take part in the bonding. Okay, that's really important for us to remember. Okay, valence electrons are the electrons that take part in the bonding. Okay, so the type of bond that forms is dependent on the difference in electronegativity between the atoms. Okay, so let's have a look at this. We have, okay, let's have a look at the different types that we have. Firstly, we have non-polar, weak polar, polar covalent, and ionic. 4 different types of bonds. Okay, and they depend on the electronegativity difference between the atoms. So as you can see for the first one, if the electronegativity difference is equal to 0, then we have a non-polar pure covalent. Okay, so let me just stop sharing my screen for 1 second. Let's just have a look. Let me get a periodic table. Let's have a look at the periodic table and see where would we find electronegativity on the periodic table. Okay, let me share my screen once again. Okay, so the electronegativity of an atom can be found on the periodic table. Okay, it can be found, 1 second. Okay, it can be found where? On the left-hand side of all the elements in the periodic table. This is where we can find the electronegativity of a specific atom. For example, let's look at silicon. It has a electronegativity of 1,8. Let's look at fluorine, has an electronegativity of 4,0. Let's look at magnesium, 1,2, and so on. Okay, I think we get the point. Okay, so that's how. So when we bond two atoms, right? For example, let's look at HCl. Okay, so obviously HCl is made up of H and Cl. So let's see if we can get what type of bond is HCl. So H has an electronegativity difference of 2,1, okay, and Cl has an electronegativity difference of 3. So we can say 3,0 minus 2,1, and this is going to give us 0,9. Okay, this is electronegativity difference. Okay, the electronegativity difference between hydrogen and chlorine. Okay, so in this case, electronegativity difference is not equal to 0. So it's not a non-polar covalent, but the electronegativity difference is certainly less than 1. So it's a weakly polar covalent bond. So the bond that forms between hydrogen and chlorine is a weak polar covalent bond. Yeah, I don't know if that's like a bit difficult to see. Maybe that's a bit better. Okay, and I hope that makes sense as well. All right, it is a weak polar covalent bond. Okay, so that's how we can determine between two elements, okay, the bond between two elements, what type of bond is it? Okay. En is equal to 0, that's non-polar covalent. En is less than 0, weak polar covalent. En is less than 2,1, but obviously greater than 1. Okay, that's polar covalent. That's when we have polar. And non-polar is defined as an unequal sharing of electrons. Polar is defined as an unequal sharing of electrons, leading to a dipole forming. Okay, we'll get to all of that in a bit. Ionic is the transfer of electrons, and subsequent, it's cut off. Okay, but nevertheless, that's fine. Okay, so that's done, right? What do you call them? The types of chemical bonds that we have, right, with respect to non-polar and polar. That's that. Let's move on to discuss bond energy. Okay, there are various attractive and repulsive forces at play between the two atoms during bonding. Attractive forces between protons of one atom and electrons of another atom. Attractive forces between protons and electrons of the same atom. A repulsive force between the protons from each atom. A repulsive force between electrons from each atom. The net electrostatic forces will determine bond strength, which can be quantified as the bond energy. This is the energy required to break the bond or energy released when bonds form. A bond energy is the amount of energy required to break 1 mole of a specific covalent bond in gaseous phase. Okay, so that's the specific definition of bond energy, but bond energy, you can think of it as when we have a chemical bond between two atoms, the amount of energy it takes to actually break that bond, okay, is the bond energy for that atom. So it's basically like, if you want to call it, the strength of that bond can be understood by its bond energy. Okay, also, not just when bonds break, when bonds form. Okay, when bonds break, energy is absorbed. When bonds form, energy is released. Okay, and this is referred to as bond energy. And yes, it would be the same for bonds breaking and releasing energy as well. Okay, so just keep that in mind. Bond energy. Sorry, yeah, bond energy. We will discuss it again when we come back to the bond length graph. Okay, let's have a look at this. Factors influencing bond strength. Bond strength is determined by bond length, okay, atomic size, and bond order. So bond length says the shorter the length of the bond, the stronger the bond. Okay, atomic size says the smaller the atoms, the stronger the bond. Bond order means the more bonds between the atoms, the stronger the bond. So when it comes to bond length, we're talking about shorter length. So the closer the bonds are, the closer the atoms are together, the stronger the bond. For example, if I had to have an atom here and one atom here, and let's say they were bonded this closely, okay, and you'll see we'll define bond length, I think, in a bit, but basically the bond that's formed between them is formed between the nuclei of each atom, just like that, for example. Okay, so let's just say we have a bond like this, and in this specific case, that's what the chemical bond between these two atoms look like. Okay, but what happens if I take this further apart and I still create a bond between them? Okay, it's two atoms of the same size, right? However, in this case, you can see that the bond formed between them is further apart. So naturally, you'd be able to understand that that's a weaker bond. Okay, so when we talk about bond length, this is what we're talking about. We're talking about the actual bond being further apart. Okay, and because it's further apart, you can understand that it would have a weaker, it wouldn't be as strong. Okay, it would be a weaker bond. Okay, let's talk about atomic size. The smaller the atom, the stronger the bond. And the reason for this is the smaller the atom, okay, the closer the bond is to one another. So let's do this in terms of an example. So let's just say we have this here. Okay, but let's make a bigger atom here. Okay. Actually, let's for the first time, let's do this. Okay, let's create a bond between atom 1 and atom 2. Okay, both relatively small in size. Now, let us use a bigger atom and create a bond with the same first atom. Okay, and see what happens. So now let's just say they're even the same distance apart, like that much. But now the distance between their nuclei is much bigger, as you can tell. The distance between their nuclei is much bigger, and naturally that would result in a bigger bond length and a weaker bond. Okay, so for the first one, we talk about bond length only. Okay, we compare atoms of the same size, right? Atoms of the same size, we can see that when they are further apart, we have a longer bond length, which results in a weaker bond. Okay, when we talk about atomic size, right, let's just say we are bonding atom 1 with atom 2, atom 1 with atom 2, okay, both of the same size. Now you can see that their bond length is a specific distance apart. But now if we take the same atom 1 and bond it with another atom 3 that is bigger than atom 2, you can see that naturally the bond length becomes longer because this atom is bigger. Okay, of course it has a bigger atomic radius. Okay, so therefore it takes like longer, if you will, to get to the nucleus of that specific atom. So naturally the bond length is longer, resulting in a weaker bond. Okay, so things that affect bond strength is bond length. Okay, the shorter the length of the bond, the stronger the bond. Atomic size, the smaller the atoms, the stronger the bond. It comes down to the smaller the atoms, the closer they are able to be together. Okay, then bond order, the more bonds, double, triple, etc., between the atoms, the stronger the bond. So this comes down to having more bonds. So we can compare again atoms of the same size. Okay, let's just say we're comparing these two. But now, if we have a single bond between them compared to a double bond. Okay, that's not exactly how a double bond would look, but just for the sake of understanding, I'm going to draw it like this. Okay, of course, double bonds would be stronger than single bonds. All right, because it's 2 compared to 1. Okay, so that's what we're comparing in the last one. It's the more bonds. So like if it's a double bond and you're comparing two of the same atoms, but one has a double bond, naturally the one with the double bond is going to have a stronger bond strength between the two atoms. Okay, so I hope that bond energy makes sense. Let's talk about bond length. Bond length, here's the bond length defined, okay? Bond length is the average distance between the nuclei of two bonded atoms. So all these bonds that we were drawing here, okay, their length would refer to the bond length, the average distance between the nuclei of each atom, okay? As the atoms get closer, the attractive forces get stronger until the minimum possible potential energy is reached, okay? This is known as the bond energy. The distance between the nuclei of the atoms at the minimum potential energy is bond length. If the two atoms get closer than the bonding length, they will be forced apart by repulsive forces, increasing potential energy. Okay, The factors influencing bond length. The factors influencing bond length are as follows: the atomic size, the bond order, and the difference in electronegativity. Okay. Let's have a look at our graph. So, process of bond formation. So we have this energy, potential energy versus distance between nuclei graph. It's a bit of a strange graph, right? It's not like an orthodox graph. Okay, but it's not difficult to understand what's going on at which points, right? And the main point is just to understand, because there's this type of graph. If they ask it in the exam, it's not going to change, right? The shape of it is not going to change. So you just need to understand at each interval of the graph what is taking place, okay, and what information you need to know. For example, let's work with it in order. We have A, okay? So as you can see, right, because this represents distance between nuclei, you can suspect that A is really far apart. A is when, compared to B, C, and D, A is when the distance between the nuclei is the furthest apart, because if this is like 1, 2, 3, 4, 5, 6, so A is at 6. So it's the furthest away from the nuclei are, the distance between the nuclei are furthest apart. Okay, so let's read up the information and see what it says. Atoms are infinitely separated. Potential energy is nearly zero. Okay, so they're infinitely separated. The potential energy is nearly zero. Let's look at B. Okay, when we are at B, right, as the atoms move closer, the forces of attraction and repulsion increase until the forces of attraction dominate. Okay, so now because the atoms are moving closer, right, they're moving closer to attract one another, to form a bond, okay, to create a bond. So let's read B again. Now, as the atoms are moving closer, so now you can see that the distance between the nuclei is less. So that indicates to us, okay, clearly the atoms are moving closer. Okay. So as the atoms move closer, the forces of attraction and repulsion increase. So both increase because they are closer. Okay, protons attracting protons, electrons attracting electrons. Those are repulsive forces, not attracting, repelling one another. Okay, so those are forces of repulsion. However, electrons attracting protons, protons attracting electrons, those are attraction forces. But when we move them closer, okay, they will increase, both of them increase because they're moving closer until the forces of attraction dominate. Let's look at point C. Okay, point C, this is the lowest, most stable energy state reached. Chemical bonds are formed. Okay, the lowest energy state now, once they are bonded, okay, it's most stable, right? There's no like uneven forces of attraction, repulsion going on. It's the most stable region. Okay, at C. Then let's look at point D. Okay, the atoms move too close, forces of repulsion increase, potential energy increase. Okay, so if they move too close to one another, they will repel one another. Okay, that's what's mentioned here. Right, remember, as the atoms get closer, the attractive forces get stronger until minimum possible potential energy is reached. Okay, the distance between the nuclei is at the minimum potential energy is the bond length. If the two atoms get closer, then the bonding length, they will be forced apart by the repulsive forces. So at point D, right, compared to point B, at point D is the point where the repulsive forces would be stronger than the attractive forces. So if they get too close to one another, they will actually repel one another. Okay, so just keep that in mind. Okay, cool. So this graph is important, right? When they asked in the exam, they asked exactly like this. Okay, so it's important for you to understand what's happening at A, what's happening at B, what's happening at C, and what's happening at D. All of them. Okay, understanding mainly also at point C, right? The bonds are formed. Okay, and then if you look, the type of energy that's at C is actually the bond energy. Okay, this is the bond energy, and this here, so this is response to potential energy. This is the bond energy, right here. Okay, that's the value of the bond energy. That's the distance of the bond energy. It's actually this distance. Okay, so no, this distance, sorry, from there to there, from 0 to there. Then the bond length, okay, is also at C. So the distance from here to here, that gives us the bond length. Because this is distance between nuclei, this is potential energy. Okay, and of course, at C, the distance between nuclei would be the bond length. And at C, the potential energy would be the bond energy. Okay, so yeah, at C is where the bonds are formed. Okay. Let's discuss covalent bonding and give it a definition. Okay, covalent bonding, firstly, you need to note that it is between non-metals. Okay, so covalent bonding is the sharing of at least one pair of electrons between two non-metals. Okay, covalent bonding is the sharing of at least one pair of electrons between two non-metals. Then we discuss non-polar covalent. Okay, so non-polar covalent, there is an equal sharing of electrons. That's what non-polar means. When we do intermolecular forces, you'll see, we'll discuss this a bit more in detail and understand what non-polar is. And we'll look at diagrams showing an equal sharing of electrons. Okay, and an obvious example of this is One second, sorry. Okay, let's continue. Sorry, someone tried calling me. Okay, so yes, an obvious example of this is diatomic molecules, because remember, in order for a bond, in order for a bond to be non-polar, okay, the electronegativity difference would need to be 0. Okay, and of course, if you're working with two of the same elements, for example, if you're working with hydrogen and a hydrogen, this is a diatomic element, H2. Okay, the electronegativity difference here is going to be 2,1 minus 2,1, which is equal to 0. Okay, so in that case, of course, all the diatomic compounds, all the diatomic molecules are going to be non-polar pure covalent bondings. Then we look at weakly polar covalent. We also did an example, HCl. Here they do HBr. They do the electronegativity difference. It's 0,7. Remember that. Let's write it here. Non-polar covalent electronegativity difference equal to 0. Electronegativity difference less than 1. Electronegativity difference going to be greater than 1. Okay, but less than 2,1. One second, sorry. Okay, so it's going to be less than 2,1, so that's polar covalent. And then obviously ionic we'll get in the next one, which is greater than 2,1 if the electronegativity difference is greater than 2,1. Okay, we have weakly polar. Then we have polar covalent, so strong polar covalent is an unequal sharing of electrons leading to a dipole forming. Okay, for the example of this is in the bond between H and O. okay, the electronegativity difference is 1,4. Okay. Let's look at ionic bonding. Okay, the next type of bonding, the next type of chemical bond. This is between a metal and a non-metal. Ionic bonding is a transfer of electrons, okay, and subsequent electrostatic attraction. So that's what was missing from the other part. So it's a transfer of electrons and subsequent electrostatic attraction. Now, what we do need to note is that we can define it as ionic bonding is the transfer of electrons from metal to non-metal. Okay, before we actually move on to ionic bonding, let us discuss covalent bonding. Okay, we'll do it in the next part with Lewis diagrams. But for now, we can just discuss it quickly. Okay, just say we have H. Okay, and now we actually want to consider how many valence electrons does hydrogen have. Okay, how many valence electrons does hydrogen have? If we remember correctly, hydrogen has 1 valence electron that it's willing to share. Chlorine has 7 valence electrons that it's ready to bond with. Okay. Right. Remember, we can determine that from the periodic table using the Roman numeral, the group numbers. So here's 1, here's 2, here's 3, 4, 5, 6, 7, and that tells us the. Let's get rid of that actually. That tells us the the amount of valence electrons that each element in the periodic table has. Okay, so if we want to determine it, we can use the Roman numeral groups. For example, let's talk about nitrogen. We can see that nitrogen has 5 valence electrons because it's in group Roman numeral number 5. Okay, so in this case, what actually happens when we combine these two, okay, they form a covalent bond. We can determine what type of bond they form by looking at the electronegativity difference. Right, let's look at the definition of a covalent bond. A covalent bond is the sharing of at least 1 pair of electrons between 2 non-metals. So here we have hydrogen and chlorine. Both are non-metals. We can confirm that they are covalent bond by calculating the difference in electronegativity. The difference in electronegativity, if we remember correctly, it is 3,0 minus 2,1. Okay, and this is 0,9. We know, okay, this between these two elements in the periodic table, they are forming a covalent bond. And furthermore, we also know that it is a weakly polar covalent bond because its electronegativity difference is less than 1. Okay, so what happens here is hydrogen and chlorine will bond, okay, and they will share electrons, right? So hydrogen, okay, the total amount of electrons that hydrogen can store, okay, in its outermost orbital is 2, okay? So hydrogen is complete with 2, okay? Most of our elements, okay, they can have up to 8, okay, and they are satisfied with 8. Once they have 8 electrons, then they are complete, okay, except hydrogen. Hydrogen just requires 2. So we in a situation here, if we look at hydrogen and chlorine, okay, hydrogen just needs 1 and chlorine just needs 1, right? To fill its orbital, hydrogen just needs 1 and chlorine just needs 1, and they would be completely filled. Okay, now what you need to know is the way that elements behave. Okay, they are always trying to fill their orbitals. Okay, if you remember correctly, these are known as our noble gases, right, in group 8. Okay, these are known as our noble gases, and these guys, they are non-reactive, okay, because their outermost orbitals are complete. Okay, they are filled. They don't have any valence electrons, basically. Okay, and all the other elements are trying to be like them. If you want to put it informally, all the other elements are trying to be like them. They're trying to fill their orbitals to complete the electrons. Okay, sorry, just 1 more second. Okay, so they are trying to complete their orbitals. Okay, so for example, hydrogen ultimately wants to have 2 electrons. Chlorine ultimately wants to have 8 electrons, okay, in its outermost orbital. So in this case, what happens, okay, is firstly, we know that it's a covalent bond. Covalent bond is the sharing of at least 1 pair of electrons between 2 nonmetals. So in this case, hydrogen joins up with chlorine. Hydrogen borrows chlorine. It's 1 valence electron, and chlorine borrows hydrogen. It's lone electron there as well. Okay, so this is how they bond. Okay, and that's how the covalent bond is actually formed. Okay, so hydrogen bonds with chlorine, they share that electron. So hydrogen sort of like shares it with chlorine, and chlorine sort of like shares it with hydrogen. Okay, I hope that makes sense. So let's move on to ionic. So we said that ionic is the transfer of electrons from metal to non-metal. It involves the complete transfer of electrons. Metal atom gives electron to non-metal. Metal forms a positive cation. Non-metal forms a negative anion. Electrostatic attraction of ions leads to formation of giant crystal lattice. Ionic bonding takes place in 2 steps: transfer of electrons from ions, electrostatic attraction. Okay, very nice. Okay, here's a nice diagram of how this takes place. Okay, electrons transfer from sodium to chlorine, so from metal to non-metal. So sodium, let's confirm that it has 1 electron, and chlorine we know has 7. So let's go to the periodic table. We can see that sodium is in the first group, first Roman numeral. So it means it has 1 valence electron. That is sodium. Okay, then chlorine, of course, is in the 7th group, Roman numeral group. So it has 7 valence electrons. Okay, but they do not form what? They do not form a covalent bond. Let us test the electronegativity difference. Okay, chlorine is 3,0 and sodium is 0,9. Okay, this is equal to 2,1. So this is a strong, no, this is not a strong polar covalent. This is ionic bond. Okay, so therefore, we can confirm it's an ionic bond. So we know that there's not going to be any sharing of electrons here. What's going to happen is, initially we have, what do we have? We have the metal, we have the non-metal, and the metal donates, it gives its electron to the non-metal. Okay. Okay, and what happens is the metal that has just lost an electron becomes slightly positively charged, and the non-metal that just gained an electron, remember it's gaining an electron, so it becomes negatively charged. Okay, so due to the formation of these charges, right, now sodium is positively charged and chlorine is negatively charged, right, opposites attract, and these two would attract one another and form a crystal lattice. I think we have a picture of a crystal lattice somewhere. Okay, I'll add it in. And I'll show it to you guys next time. But yes, ionic bonds, you need to know a little bit of the theory as well. They do form a crystal lattice, which actually is a strong bond between the two. Okay, the crystal lattice is actually very strong. Okay, so keep that in mind. Let's look at metallic bonding. Okay, so metallic bonding, you just have to understand the theoretical aspect of it. Metallic bonding is the bond between the positive metal nuclei and the sea of delocalized electrons. The metal atoms release their valence electrons to surround them. There is a strong but flexible bond between the positive metal nuclei and the sea of delocalized electrons. Okay, so these are when we have 2 metals bonding. Okay, so the key thing here is you need to understand that the definition, to be honest. Metallic bonding is the bond between the positive metal nuclei and the sea of delocalized electrons. Okay, so what happens? How do those delocalized electrons form? The metal atoms release their valence electrons to surround them. Okay, that forms the sea of delocalized electrons. there is a strong but flexible bond between the positive metal nuclei and the sea of delocalized electrons. Okay, let's look at this. Lewis diagrams. Molecules and their atoms that are made up of let's move closer. They are made up of, molecules and the atoms that they are made up of are extremely small and cannot be seen with the naked eye. Models are used to visualize the atoms and chemical bonds between them. One of the ways that we visualize chemical bonds is by means of Lewis diagrams. Lewis diagrams show the valence electrons around the nucleus represented by the element symbol. Example, give the Lewis diagram for the following symbols: lithium, carbon, and fluorine. Okay, so let us do this ourselves. Let us do magnesium, aluminum, and boron. Magnesium, aluminum, and boron. So magnesium, we can see that it's in the second Roman numeral group. So it basically has 2 valence electrons. Valence electrons, they can be represented with dots or X's. Okay, so this one just has 2. The way you draw your valence electrons, okay, you never draw both here, for example, never. You always start by drawing 1 on each side at least. So we have 1, 2, 3, 4 sides. Okay, so we always want to go in order. So let's just draw it with circles. So I want to start here, go there. Okay, it doesn't matter if you're going clockwise or anti-clockwise, but you want to always have 1 on each side at least. So, okay, this one doesn't have more than 2. So I can draw 1, 2, for example. Okay, and now I've represented what? I've represented the valence electrons, the Lewis dot diagram of magnesium. Right, let's have a look at aluminium. We have to first determine how many valence electrons does it have. Aluminium has 3. Okay, let's not do boron, we're going to do sulfur. Okay, aluminium has 3. So again, we start off by drawing at least 1 on each side, and aluminium has 3, so we're done. Can even go that way, it doesn't really matter this. Okay, so aluminium has 3. Let's go back to our periodic table and let's look at sulfur. Sulfur has, that is 6. It's in the 6th Roman numeral. So it has 6. So let's go back to draw it. 1, 2, 1, 2, 3, 4. Now I start forming the double bonds. Sorry, not the double bonds, the pairs. 5 and 6. 1, 2, 3, 4, 5, 6. And that is how we draw. That's how you basically draw the Lewis dot diagram for a single element. Okay, throw at least 1 on each side. At least 1 on each side, basically, right? And that's how you go. You don't start by drawing 2 on one side. 1, 1, 1, 1, as many as you need. Okay, so sulfur has 5, 6, sorry, and that's how we draw it. Okay, so here they have lithium. Lithium has 1, carbon has 4, and fluorine has 7. General steps to drawing Lewis dot diagrams. Lewis diagrams can be drawn for a variety of molecules by using the following general steps. Choose the central atom, the one with the lowest electronegativity found on the periodic table. Determine the total number of valence electrons. Put 1 shared pair between the central and terminal atoms. Arrange the remaining electrons around the atoms so that 8 electrons are placed around the terminal atoms, except hydrogen is equal to 2 electrons if they are. Okay, wait. Okay, put 1 shape. Okay, arrange the remaining electrons. Okay. If there are not 8 valence electrons around the center atom, move some of the electrons between the atoms to form multiple bonds. Okay. Give the Lewis diagram for the carbon dioxide molecule. Okay, so now we've learned Lewis dot diagrams for single elements. Okay, magnesium, aluminium, sulfur. These are easy. Why? Because okay, they are just for a single compound. We just need to know the amount of valence electrons that each of them have, and then we draw their respective valence electrons with dots or X's around a symbol, and the symbol is basically the element. Okay, the element symbol, right? The chemical symbol, that's what we use, and we draw the valence electrons around them. Okay, but now what happens if we have to draw a compound like carbon dioxide? Carbon dioxide. They want us to draw the Lewis dot diagram of carbon dioxide. Now we're going to do many examples. Okay, in fact, I'm going to give you guys a list of Lewis dot diagrams that I want you guys to just know, like memorize. Like, okay, you need to know these 10. Okay, at least know these 10. These are like maybe common ones from past papers, right? I'll just have a list that I'll give to you guys that you should know either way, whether you understand it or don't understand it. At least learn those. Okay, so carbon dioxides. Let's follow the first step. Lewis diagrams, blah, 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 blah. Okay, choose the central atom with the lowest electronegativity found on the periodic table. Let's compare carbon and oxygen. We can clearly see that carbon has the lower electronegativity. Okay, since carbon has the lower electronegativity, we are going to draw it in the center, because remember, this carbon is bonded to oxygen. So it's going to have oxygen bonded maybe perhaps on either side. Okay, so let me just think. Okay, before we do carbon, let's do H2. I think it will be a bit easier. Okay. Yeah, I think this will be a bit easier to start off with, and then we can do carbon dioxide. Okay, so let's compare hydrogen and oxygen. Okay, in this case, we can actually see that hydrogen has a lower electronegativity compared to oxygen. Okay, however, if you're going to put hydrogen in the middle, okay, it would be able to bond, but it doesn't. You see, the step number 1 doesn't work in all cases. Okay, so that's why their steps I'm not really keen on them. This, okay, but we'll make note for now. This doesn't always work. Okay, it won't always work to choose the central atom. These are just general, okay, this is a keyword. These are more like general steps, okay, like generic general steps to solving the Lewis dot diagram. Okay, but that's what I'm saying. I feel like the better way to learn it is just to do a few more examples to get the hang of it, okay, and do all the basic examples and know how all the basic examples work, right? So yes, let's look at hydrogen and oxygen. Okay, so this is again a common example which you should know, right? Okay, maybe not now, but by the end of this lesson at least, by the end of this topic, when we're done with this topic, right? But when we have hydrogen, okay, two hydrogen bonded to oxygen, right? Let us consider hydrogen, okay, and let us try and figure out, okay, how will this actually bond? Okay, so if we think of hydrogen, hydrogen has 1 valence electron, while oxygen has, let's go and see. Okay, oxygen can be found here, and it has 6 valence electrons. Okay, that's how we know how many valence electrons it has. So oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Okay, I'm going to draw it like that. So oxygen has 6 valence electrons. Okay, so what's going to happen here is, because we have, so if I had to ask you, how many electrons does oxygen need to be in its complete state? Okay, how many oxygens does how many electrons does oxygen need to fill its orbital completely? The answer to that would be 2. Oxygen needs 2 valence electrons to fill its orbitals. Okay, it needs 1 here and it needs 1 there. Okay, and if we consider hydrogen, hydrogen comes in with 1. Okay, hydrogen comes in with 1 electron. Okay, and therefore hydrogen can slot in there and share 1 of its electrons, okay, to complete oxygen, okay, just only on one side, right, to complete oxygen, like that, okay, and it will use 1 of oxygen's electron to complete its own orbital, right? Remember, hydrogen just needs 1 valence electron to complete its orbital, okay, and that's why 1 oxygen forms there and another oxygen forms there. That's why we have two hydrogens. Okay, so in this case, our central atom is going to be oxygen. Okay, so in this case, our central atom is going to be oxygen. Oxygen has 1, 2, no, let's work this way. 1, 2, 3, 4, 5, 6. Okay, and hydrogen comes in, it bonds, okay, with one of the sides of oxygen. Okay, remember oxygen, oxygen. Okay, it has this single electron that's ready to bond to create to form a pair. And here, hydrogen, the second hydrogen comes in, and it forms a bond with oxygen using this single electron here. Okay, and what happens here, this can be represented slightly differently also. Okay, if I just want to do it like this, doesn't matter, that's fine. It forms a bond, and like this forms a bond. Okay, oftentimes you will also see this forming a bond, and what this bond represents is actually 2 electrons. Just keep that in mind. Okay, so these are all but this is the way you should answer it in the exam. This is the Lewis dot diagram, if you ask for the Lewis dot diagram, that is. However, if you see in a multiple choice or anywhere else, if you see it like that or like that, those are both fine, won't be incorrect. Again, they mean the same thing. Okay. Yes. Okay, so just before we took a structured approach, before I'm teaching you a structured approach to answer these, I just wanted to do one. Okay, so that you're also not just following a process of do step 1, do step 2, do step 3, and so on and so forth. Like you're also understanding the logic behind it. Okay, and that if you ever get into something where maybe your steps are not working or you're confused, you can maybe use logic to get your way out of it. Okay, so this here is oxygen bonding with hydrogen. Let's look at carbon dioxide. So carbon dioxide, when we follow our methods, you will see that carbon dioxide, okay, has the lower electronegativity and it becomes the central atom again, but it's not the case for oxygen, right? If we compare oxygen to hydrogen, oxygen has the higher electronegativity, but it's a central atom. Okay, so just keep that in mind. That's not always the case. However, if we're going to utilize our logic, our brain, I hope we have that. We're going to look at carbon and we're going to look at oxygen. So we know that there's 2 oxygen and 1 carbon. So now we're going to try to see how does this bond. Okay, so carbon has 5 valence electrons, while oxygen has 6 valence electrons. Sorry, carbon has 4 valence electrons, while oxygen has 6 valence electrons. So we have this carbon atom with 1, 2, 3, 4. Okay, then we have 2 oxygens. We only have 2 oxygens. Okay, 2 oxygens. We have this guy. What did we say it as? 6. 6. Okay, sorry, just give me 1 second. I'll be back in a minute, like 30 seconds. Okay, so I'm back. In this case, right, we have 2 oxygens. So you can even draw out your 2 oxygens. Okay, and the same as that. Okay, so we have a carbon, okay, which requires, okay, this is what you always need to understand. How many valence electrons? So how do you determine the valence electrons? How much an element has? Okay, so that's on the periodic table. Okay, how do you determine the valence electrons? Okay, that's from the periodic table. So here is our Roman numerals: 1, 2, 3, 4, 5, 6, 7. Right? We don't consider these numbers, the English numbers, just Roman numerals. Okay. and 8. Okay. So how do you determine valence electrons? That is the question. You follow those group numbers. So all the elements in group 1, Roman numeral group 1, have 1 valence electron. All the elements in group 2 have 2 valence electrons. All the elements in group 3 have 3 valence electrons, and so on. These have 4 valence electrons. These have 5 valence electrons. Okay. These have 6. Okay. These have 7. Okay. And these, in fact, do have 8. Okay. And that's why they complete. That's why they're non-reactive, because they have no valence electrons. And remember, valence electrons are the ones that take part in bonding. So since they have no valence electrons, they have no electrons that take part in bonding, they are very stable and they are non-reactive. Okay, so that, I hope that answers your question as to how do you determine how many valence electrons each element has. You just simply turn to your periodic table. Ooh, time is over, but it's okay. Let's just finish up. Okay, so in this case, like I said, we have these 2 oxygens that we need to bond with carbon. Now, carbon, it needs 1, 2, 3, 4 valence electrons to fill its orbital. While each oxygen needs 1, 2. 1, 2. Okay, so let's try and align this, right? If we're going to try and form a bond between oxygen and carbon, okay, let's just say we bond here with oxygen. Okay, this doesn't make sense because I'll show you why. Let's just say I'm forming this one bond between the 2. Okay, let me just represent it slightly differently. Let's do it like this, so we can see that one is coming from oxygen, one is coming from there, but they use both. It's called a bonding pair. Okay, for example, let's look at this. Okay, so now we've created a single bond between carbon and oxygen. However, things are looking a bit weird. Okay, so firstly, let's learn some terminology, right? This here is what we call a bonding pair. Okay, it's called a bonding pair because it is a pair of electrons that are used to bond 2 different elements. Okay, and they share those electrons. For example, oxygen is going to use the O and the X, and the carbon use the O and the X. Okay, so in this case, right, there's many things that, okay, so this is the bonding pair, by the way. Then we have a lone pair. Okay, a lone pair is a pair of electrons that is extra. Basically, it does not take part in the bonding. Okay, and as you can see, those 2 for now, they don't take part in the bonding. Okay, that's another thing, right? Now, there's a few things that tell us that there's something wrong with this diagram. Okay, the first thing is you should always, whenever you're doing Lewis dot diagrams for compounds, you should always check what? You need to check the total amount of electrons after bonding that each element has. Okay, and you will count the bonding electrons as well. So for example, for carbon, I will count all of these. So carbon originally had 4, but now because it's sharing those 2 with oxygen, it has extra 2. So now it has 6. That is not complete. Carbon is not complete. Carbon wants 8. Let's look at oxygen. 2, 4, 6, 7. That's an odd number, even worse. Okay, so clearly there's something wrong with this diagram, and the total amount of electrons in each orbital is not adding up to 8, or in the outer orbitals of each element is not adding up to 8. Okay, so in that case, this is what we should try and do, one of these steps. Okay, they say if there are not 8 valence electrons around the center atom, move some of the electrons between the atoms to form multiple bonds. That's exactly what you should do. In a specific case like this, right? When you have extra electrons like this and like this and like this and like this, there's no use keeping them extra, because firstly, it does not complete the orbitals. Because there's 1 electron here, you're never going to be able to get an even number of 8. It's always going to be an odd number. Okay, so it's not going to complete your orbitals. In this case, what you should try and do is rearrange your electrons to form double bonds. So what I'm going to do is Okay, I'm going to move one of this here to get it for bonding, one of this here to get it for bonding, and then these two, they're going to move here to bond with the carbon. Okay, so now we formed a double bond on each side. So it kind of makes sense, right? Because look here, you have each carbon needs 1, 2, which can bond with 1, 2. Then it needs another 1, 2, which is going to come from 1, 2. Actually, let's do it like this. Okay, so the carbon needs 4, and each hydrogen needs, the carbon needs 4, and each oxygen needs 2. So that makes sense, right? One oxygen bonds on one side with 2 of the carbon. That makes that oxygen 8. The other oxygen bonds with the other side of the carbon with the other 2, because the carbon has 4. Okay, and it makes it 8. And then when you finally check your carbon in the center with its bonding, because now that it's bonded, the amount of valence electrons, you count it with its bonding pairs. In this case, it's 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, and that's how you form the Lewis diagram for carbon dioxide. Okay, so before we follow any formalities, there are some easy examples that we don't even think we solve them in this way. It's like these, honestly, like you should know, you should like by heart these. These are very common examples. Carbon dioxide, hydrogen, water, H2O, these are easy examples. And then we will do some other examples, but also, yeah, okay, there's also like a standardized method that you can follow. But before we discuss any of that, I just wanted to do some examples so you can get an understanding of it. But yeah, okay, let's end it there for now. I hope that you guys understood. If you guys do have any questions, I'm going to leave it open for a little while. And yeah, I'm going to do that. Okay. Also, I haven't been like really, I don't think so. Maybe I did last week, but if I don't end up sending the message that your drives are updated, just assume that your drives are updated, because I always update them immediately after the lesson. So yeah, I just tend to send the message late sometimes. But yeah, okay, I'll leave it open for like the next 2 minutes. If anyone has any questions, please feel free to ask. Okay, it doesn't appear that anyone has any questions, so let us end it there. Jazakallah so much for joining. Jazakallah khair. I will see you guys next week. Okay. Assalamu alaikum.